hats to get solutions to harder problems.
It's bracket, right? Or is that what you use?
Yeah. All right, so that's one thing. So these are like, these solutions are like the I hats and J hats. Okay, the other thing is that they also have all the properties of vector spaces. All right? In other words, there's a condition of orthogonality of being perpendicular. All right? And example, the integral of cosine of 3x times the integral of cosine 4x dx equals 0. So that's just like I hat dot j hat equals 0. All right, so there's a condition on functions that is just like a dot product. All right, in function space it's called an inner product. Inner product. Yeah.
Just a quick question with that. Like, I understand the integral from negative to infinity of these two functions equals 0, and that shows that orthogonality of them.
Yeah.
But I guess I always thought about something being orthogonal as like x. And then
Right,
y,
because
like,
you're not making a transition. It's an analogy. This is a completely different space.
yeah, like,
You're dealing with a physical space you can touch this way and that way.
right.
All right? I'm asking you to throw away that and just use that as an analogy. Here's some make-believe space.
Just look at the mathematical properties of the space. Like,
Yeah,
for instance,
it just has to do with the properties. If I call I hat dot j hat 0, right, in vector space, but now in function space I'm going to say, no, this is what the dot product is in function space. And if the integral of that thing is 0, that's I hat dot j hat. Alright, so it's an abstraction. It's an abstraction into this function space. And what you can show is it has all the properties of a vector space.
like you can do cross products. Yeah.
Alright? Interesting. I don't know the answer to that. I only know the dot product. What's that?
I guess I was trying to maybe not abstract in some ways. Is there anything not to make abstract?
I don't know. You tell me. The way I always do it, when I do it in more details, I really build a vector space where you have a physical field. And then I show that these functions, this is a dot product in function space. If that dot product equals 0, it has a dot product equals 0 between different bases in that vector, in that function.
Condition is so perpendicular.
Yeah, and so it's orthogonal.
So
And well, I guess in linear algebra, you can show that two vectors are orthogonal by constructing the reduced row echelon matrix. You put these in Gaussian form. You put them in a matrix, and you Gaussian eliminate, and then you get reduced row echelon.
Right.
And when you get to reduced row echelon, you can say that these are linearly independent. So I hat and j hat are linearly independent. Okay? Here, you can use the same type of analysis and same type of math to show that cosine of 3x is linearly independent of cosine 4x. So the idea, I guess, the connection between them is the idea of linear independence. That these vectors are linearly independent from each other, I hat and j hat, when these functions are linearly independent from each other. Okay? So, Matt, what were you going to say?
So if you have two functions that are integrable over all space,
Yeah?
the inner product of those two functions, and it equals 0,
Yeah?
the inner product of those two functions will also equal 0.
And 0. And so, in other words, you can think of those two functions as being perpendicular.
No.
And
But what does perpendicular really mean? What does perpendicular really mean? Perpendicular really means that they're linearly independent from each other. That's the connection.
So quick question, in that case, then when they're linearly independent, it's 0. But in this case where the probability adds to 1, is that the same as saying that they're linearly dependent or they're parallel or?
Well, certainly like our cosine 3x and cosine 3x has to equal 1. It's like a dot product like I had.
Yeah.
What's the benefit of being linearly?
Oh, okay. Okay, so the first benefit is that once you have a basis set, you found a nice I hat and J hat function space. And those are the easy answers. You can build complicated answers out of it. All right? That's the first big thing. But the second big thing is once you have complete function spaces that have all the properties of vector spaces, and notice, not all complete basis sets have all the property of vector spaces. Everybody got that?
What was that again?
So, not all complete function spaces have all the properties of vector spaces. So, not all vector space, not all complete bases have this property. So you could have complete bases like polynomials, x squared, x cubed, x to the 4th, and so on. Polynomials form a complete basis. Polynomials of order n form a complete basis in function space. I can expand anything in terms of polynomials, x to the 0, x1, x squared, x cubed, and so on. But the integral of like x squared dx certainly does not equal to 0. So polynomials do not have the properties of vector spaces. You can put polynomials together in special ways called Legendre polynomials. Sound familiar from math? And when you put Legendre polynomials together, the Legendre polynomials have all the properties of vector spaces. But I'm saying too much math here. The point here is, Matt, that for complete basis sets of functions that also have all the properties of vector spaces, those are given a special name, and those are called Hilbert. These are Hilbert function spaces. All right? Now, if you have a Hilbert function space, it means your functions behave like what?
Vectors.
Like vectors. And if your functions behave like vectors, you could represent this whole thing with wave functions, not in terms of wave functions, but you could represent them in terms of matrices and vectors. And if you put them in terms of matrices and vectors, you are now not doing Schrodinger's wave formalism. What are you doing? You're doing Heisenberg's matrix mechanics.
So if you have a complete function that on a complete basis that you have a Hilbert space?
No. So, not all complete function spaces have the properties of vector space. So you also have, for complete function spaces, you also have to show that they have all the properties of a vector space.
Okay.
Which means that they satisfy this inner product, which is the dot product condition. All right. Now, Schrodinger's solution to Schrodinger's wave equations indeed are complete bases, and those solutions to Schrodinger's also also have all the properties of vectors. Therefore, solutions to Schrodinger's equations are all Hilbert spaces. So, guys, what type of world do we live in? Hilbert function spaces. What are Hilbert function spaces?
Well, they have to form a complete basis set.
Complete basis and
Have all properties of vectors.
have all the properties of vectors. All right?
So in order to show a complete basis that has all the properties of a vector space, that the integral over all space has to be
It would,
0.
it would be like the integral of f of I times f of j dx. I mean, if I were to write it mathematically, Matt, it's
Yeah.
something like this. Minus infinity to plus infinity of f of I of x times f of j of x. What do you think, guys?
Zero.
Would equal 0, and now I have some conditions. I would agree 0 for I, what?
I is equal to j.
I equal j?
No.
Not equal to j.
I not equal to j. And then 1 for I equal to j. Okay? And that preserves the dot, so that's the function space version of a dot product. And the function space version of the dot product is called an inner product. So an inner product in function space is just really a what?
Dot product.
It's like a dot product in vector space. Alright? What is it hoping to tell you? Orthogonality. Orthogonality has a very physical interpretation, and if you want to drop the physical interpretation, what could you say? Linearly independent.
Yeah.
Got it. We did linear algebra probably like you've never seen it. Right? And more. What time did we go to? 5 minutes ago? Man. Alright, so look, I didn't get to go over those homeworks, but we're essentially done with that chapter. Alright, and guys, so the goal is we are now going to try to solve Schrodinger's